I'm just going to give a talk about this year's Nobel Prize, and it's mainly about metal organic frameworks. I have some experience in them, so I think I can talk about the usefulness and their potential use in the future also. Okay, this is like the most basic understanding of what a metal organic framework is. As I go through this talk, you'll understand it's just basically coordination chemistry. All of you must be familiar with coordination chemistry. I think if you've done science in the 11th and 12th, you've definitely encountered coordination chemistry, but a more extended way of looking at it. Like you can extend it across 3 dimensions, going beyond Werner's complex. So I've titled it this way, metal organic frameworks, porous powerhouses for all that room at the bottom, because these materials have very enhanced surface areas. Like some of the MOFs that I'm going to show you, they have surface areas of at least 4,000 meters squared per gram, and there have been materials made that have much higher than this. So they can contain a lot of gas, they can capture a lot of chemicals and gases. And to give you an understanding of what 4,000 meters squared per gram is, roughly the size of a football field, the average area of a football field is around 9,000 meters squared per gram. So like 9,000 meters squared. So 2 grams of these materials can hold that much space. Okay, so they're very good for gas capture. At least that's the main thing, and then I'll show other applications. So yeah, these 3 people have independently contributed. I will talk about the role of each of them first before going on to what MOFs are actually and how they find application. I will just talk about a few applications, especially about gas capture, catalysis, and removal of toxic chemicals like removing uranium from water, seawater for instance. Okay? So each of them has made a very significant contribution and made sure that they clarified that this is a big deal for chemistry, for material scientists everywhere, especially given the materials that we already had before. Okay? Of course, the person who started it all is Richard Robson. I will talk about his seminal papers. Each of these people, I will talk about the seminal papers that began their actual research into MOFs and eventually covalent organic frameworks also. So yeah, typically before MOFs were discovered and before you had these coordination polymers discovered, at the most we had synthetic control over like 1D networks, like say polymers. We know polymerization reactions, and to some extent you can do them with some control, right? But there was not much advances in making these 3-dimensional materials. 2D also very little advances were made. Okay, so it is a big thing that we couldn't do these 3D networks as efficiently, like with predictive. We have 3D materials in your metals and all this. You have crystal lattices and all this, but there you don't have much control. You're not designing things to make it the way you want it. Whereas this kind of control that you have in, say, polymerization, in linear polymers and all these, what the industry has done for all your plastics and all this, we don't have it for 3D solids. At the most, we have these naturally occurring materials called zeolites. Zeolites are found in deposits everywhere, and there are ways to make it, but they're typically made of only aluminum and silicon linkages. Okay, and they have aluminum silicon bonded through oxygen, and they have fixed pores. They are very rigid. They're very good for the industry, like the petroleum industry, if you want to do cracking and if you want to break various components of your gasoline, or if you want to, all the fractions that come from the oil field, if you want to break it down into more useful gasoline, these zeolites have been serving us for a long time, almost 100 years, maybe more. But they are very rigid. You cannot design them, you cannot tune them the way you want to tune them, and you don't have any structural control. Most of the time when you make zeolites, they're made hydrothermally. You put all the ingredients, you put like the potassium source, you put the sodium source, and you put the silicon source, you put it in a high temperature vessel, and then you open it, you don't know what you might get. The crystallinity varies, you have to do trial and error to get the crystallinity of these particular materials. And their pore size is also very fixed. Okay? So until in the initial stages of when MOFs and KAUST came, they were always compared to zeolites. Almost every person, even when I was doing my PhD in the US, they kept asking like, why do you want to make these MOFs when we already have zeolites? Especially these zeolites are stable up to like 1000 degrees Celsius. Okay, so the role that these 3 people had to play to make sure that MOFs were acknowledged as being even better sometimes than zeolites, they had to do a lot. It's almost like 25 years of work, and especially Omar Yaghi and Susumu Kitagawa, they put a lot of effort into doing this. So the earliest known understanding, the maximum we understood about, like, 0-dimensional, we had like Werner's complex. You had coordination compounds where you had a metal coordinating with some ligand. This is known, and we've always known it, and like many of these coordination compounds exist. And this is the earliest instance of such networks, the Prussian blue, where you have this 3D linkage across this iron and cyanide compound, cyanide ligand. This kind of forms a three-dimensional network, but this is about the only thing that existed. Then we had clathrates, where you had some things coming in through interactions, so like some weak interactions, they would come together and form these cage-like compounds. Okay, and this is known as the Hoffman clathrate. All that this would do is like you had 2D layers of this type, and in between these 2D layers, you can have a benzene ring, like you can have a benzene compound. Like these are the earliest known, you can say about extended networks in inorganic materials. Okay, but not much progress was made until what Robson did. So this is the first reported paper of MOFs. It is not called MOFs back then. There are two papers that he and his student, his PhD student Bernard Hoskins released. They both came in 1989 and 1990, and it was the first instance of using a complex ligand to form a very long extended structure. Okay, they used copper, and they used this particular ligand, tetraphenylethane. That is the thing that you see these four things set here. It's like an intercross ligand. Okay, it's like this. So that's the unit you see here. So they started calling, and this whole thing that you see here is just, each one of these is a rod also here. So it's like a building unit. And when you mix these compounds, very readily they form. You don't have to put too much temperature, or you don't have to put too many conditions for it to form, crystallize and form an extended solid. Okay, and you can change the amount of this that is there. If you don't put the right amount of this, you can probably get some defects in the structure. So if you put the correct molar ratio, if you put the correct stoichiometry, you can get these extended compounds. You can get very fine crystals also, not requiring too much effort to make these. Some of them happen at like room temperature itself. Okay, it's just coordination compounds, but now you have structural order that you would not have seen before. Okay, so this is the first reported compound, and then using this, so he was just doing this as a hobby. He was not doing it to, and when he made this compound, even after these two papers were published, a lot of scientists said this is completely useless. It has no value. Okay, but the point is he pointed out a very important thing, that each of these things has a huge cavity. Okay, like when it forms, normally when these solids form, they form interconnectedly, and they don't have a gap in between. Like earlier when they were trying to make these compounds with zinc cyanide and copper cyanide, what would happen is you would have these adamantane cages of these zinc and cyanide interconnecting with each other, interlinking with each other and leaving no space. But this is the first time when he made it, he got this huge void. There were portions where there was nothing there. There was volume to fill it with. So, and he had even noticed that when he started off with this BF4, when he had made this compound, initially in the spaces of these voids, there was BF4 as a liquid. It was present there. But then when he tried with another liquid, when he replaced it, it completely removed this, and it PR3 or I'm not sure some other liquid, it completely replaced this inside. So then he saw the potential for these things, that when you make these kind of solids, you have these voids, you can probably store liquids, preferentially store gases, preferentially store anything else. This will, it was in 1989 and 1990, okay, but the implications are very wide for us even now. For example, these kind of materials are what can potentially store hydrogen fuel. If you are taking your cars and you want to try and store hydrogen as a gas cylinder, it's very difficult because you have to pressurize it to at least 140 to 150 bar, and that's not feasible for most cars, right? So this is the first instance that these kind of voids can store either liquids or gases. Okay, but of course people just junked it, and one problem was in the earliest days you could make this, but eventually it would crash. Like all the ligands would come apart, it would disintegrate. It was not very stable beyond in certain solvents, and then it was not stable to temperature. But when they did this and for the crystal determination, they could get this compound for some time, and they could say that it exists at least reasonably well. It's just that it was very conceptual at this point. Okay, but this work, both these papers, inspired both Susumu Kitagawa and Omar Yaghi to pursue this at a much more rigorous scale.
Okay. The structure would crash. Is it a spontaneous crashing?
No, it's like
something triggers that crash?
Something will trigger. Basically, if you use an acid, or if you heat the water to say 60 or 70 degrees. Even the first instance of whatever Susumu Kitagawa did, it was like this. They were like not very stable. See, now if you want a MOF to really be applicable in many scenarios, it has to be hydrothermally stable, especially steam or water is coming. Some of these MOFs were not even, like if you heated the water slightly, it would just the whole crystal order would come apart.
I was just wondering, you said that BF4 was trapped inside.
Yeah.
So supposing you remove the BF4, does it?
No, that time it was okay. But then I think when they were trying with other solvents or whatever, like if you put in methanol or some other solvent, sometimes it would disturb the linkages. The linkage between the copper and the cyanide part of this tetraphenylethane probably was not strong enough. There were things that had to be. So the earliest MOFs that were made, this MOF at least, It was just a direct coordination between the copper and the ligand. So it was not apparently not that strong, and it couldn't sustain for long times. So, but he was just interested in making these models. He was just interested in showing these things that you can do something with them, and you can probably see some future in them. So yeah, so like they came apart quite easily, and so most people just junked it, said, okay, this is just a nice fun thing to look at, and maybe do it as an undergraduate project, but not look at it further. But then, Susumu Kitagawa, he was also at the same stage where he was trying to make a lot of these materials. If you see all his earlier papers before this, if you go to Google Scholar, I went and did the survey, all his earlier papers were in okay journals, not that great, because he was having the same problem that Robson was having. All these coordination linkages were not so strong to be able to sustain, right? But this is the first time where you could make this breathable morph, okay, where it could rotate and these channels, interlinking channels. If you look at this, there's a channel A and there's a channel B, which are like orthogonal to each other. And they could basically move with the way the gases are flowing in and out of them. It is not that stable, but it was more stable than whatever was happening before. And it was stable at pressure also, okay? So they could trap these gases and potentially see that, this is stable, the structure was still stable after use. Especially in the case of CH4, if you look at the adsorption isotherm, once it accepted the gas and once the gas desorbed, it was still okay. And when they did the XRD for it, the structure was still the same. Okay? So this is like the first instance where Kitagawa showed that, these morphs can particularly be made more stable than what was previously known. Okay? And even then people said, zeolites are there, why are you doing this? And even this kind of morph, it was not stable, thermally stable, say, beyond 175 or 200 degrees Celsius. So the use case scenario was not yet evident at 1997, right? So after this, he followed it up with a review where he showed the different generations of morphs. So this is the first generation where you could make these layers, okay? But when the gas is adsorbed, and then when you wanted to release it, either when it's adsorbed or desorbed, it broke apart. Like the morph, the gas couldn't be contained. The structural integrity of the morph was not that strong. In the second generation, where you made these stable morphs, okay, they could adsorb and desorb, but they were kind of rigid. They were kind of like zeolites still. But now, there are many morphs where you can trap gases and you can prevent them from going back out. You can change the movement of the linkers. Most of these linkers are rotatable, around a bond. I'll show you some examples that will be more evident. But basically, you can make these flexible morphs. So they had to show he had to write this paper, the Bulletin of the Chemical Society, where he's detailed the many advances that happened by the time they came to 1998 on these morphs. And then they can be applied to scenarios where zeolites would never be used. Like a zeolite can never do this. A zeolite is rigid and it has a very fixed role. And it cannot, most of the times, a zeolite cannot separate gases that well. You cannot change the internal coordination environment to change what kind of gas it attracts to or gets bound to. So this is the paper that Yaghi published. That is his first instance of actually showing these linkages. Okay, they made these 1,3,5 tricarboxylic acid type of linker. So typically, what happens is you have a linker and you have a metal node. Okay, in this particular case, the metal node was, I think, zinc. They had a zinc metal node. So you'd form these linkages across. This would be extended across a layer. And then you would have a pyridine molecule holding a secondary layer. Like in between one flat layer like this, you'll have pyridine molecules holding these layers together. Okay? And the good thing about this kind of structure, it could selectively hold only aromatic compounds, no aliphatic compounds. So if you put an aromatic compound into it, because of pi stacking between these two layers and say whatever's in between, you can have this pyridine or some other aromatic compound held between it. You can separate aromatic compounds from aliphatic compounds, like as long as you had some kind of pi stacking. Okay, so this is like the top view of the same thing. Like you have a top layer, then you have pyridine in between this layer and another layer, and you can trap them like that in that sense. Okay, so this is published in Nature. So now after this, people started taking it very seriously, and he was the one who coined the term metal organic framework. To Robson, it was just coordination polymers, right? But when you do this, people start taking notice and realizing, okay, this is something more than what a typical coordination chemistry does. Okay, so now one of the biggest problems was all these morphs, they were not very thermally stable. Even this one was like, somewhat not good at high temperatures, like even about 200 degrees Celsius, it would not stay, it would not have its structural integrity. Okay, I mean back then this is a big deal that it was stable up to 300 degrees Celsius. Now you have MOFs which are stable up to 700, even 600 and 700 degrees Celsius. Like they are approaching the kind of stability we've seen from zeolites. Okay, but this MOF was the first one. It had almost a space of 2,900 meters squared per gram. Okay, to give you a scenario, 3 grams of this will contain the space that you have in a football field. Okay, so this was where you had a zinc node and you had these oxide linkages. You had the zinc oxide cluster, and the zinc oxide cluster would bind to this benzene dicarboxylic acid. You'll have two COH groups on either side on the 1,4 position, and they will form this strong bond between the zinc and the carboxylate group. Okay, so then these clusters together will form an extended solid, and it was very easy to make these MOFs. Okay, see the thing about all these metal organic frameworks was actually finding what combination of linker, this is called the linker, and the node, the oxide node. Earlier it was when Robson made it, it was just a single metal ion, but in the case of this MOF 5, it was zinc oxide cluster. Typically most MOFs now, the most robust MOFs will use some kind of zinc oxide cluster, and there'll be a lot of coordination chemistry involved in between them coordinating with the organic linker, and the strength of that bond is what determines the integrity of the MOF. Okay. Yeah, so then one more thing was, see, what you can't do with zeolites is, see here there was a certain space, right? You had like 18.5 angstrom. If you wanted to make this space bigger, you can make this a double linker, make it like a bipyridyl, increase the length of the chain of the linker. So when you increase the chain of the linker, you can make more and more space. The voids become larger and larger, and then you can have more and more space to occupy different types of host-guest interactions. Okay, so again, Yaghi did a lot of work to show this, and it was possible. Of course, it was published in Science. This is published in Nature and then in Science, where they showed by increasing the length of the linker, using the same zinc oxide tetrahedra arrangement, along with these linkers, they could increase the space, how much you can try to capture or occupy in that space. Yeah, so that's about, so these three people, they started this going, they started the ball rolling, and then after them, like this is another paper, this is one of the most popular used MOFs, even we used this when I was in Iowa State. This is very good for catalysis. Basically, you can tune the linker and even the functionalization on the linker to have it capture CO2 more or capture platinum nanoparticles. Like we use it to capture nanoparticles and make very high loadings of nanoparticles and increase their surface area. Typically, if you see most of the supports in catalysis, like I say in any industry or whatever, they'll take silica, which is very easily available, right? Porous silica is very easily available. And when you put metal, you can at the most put like 1% metal loading. And then you have to put a large amount of the catalyst to do it. In these kind of MOFs, because of this contained environment, you have these porous, each of these MOFs is one unit. It's like an extended network where you have all these small holes of a certain size. You can design the size you want. You can control it, and making these MOFs is not very hard.
What is the surface you're talking about? Can we see it on this image or not?
Which one? The surface?
The surface, you're saying it's as big as a football field.
Oh yeah, I mean you can't see it on this. Basically what I'm saying is this pore, right? Like if I take 1 gram of this particular material, the kind of volume that it holds inside one linkage like this, I mean like the whole MOF, like a 1 gram of that MOF, will be equal to the space, the surface area of a football field.
You're saying the volume is equal to
I mean like you convert it to surface area, like the kind of, the space that is within that volume, right? Those pores, if you were to convert it into surface area, it would have the equivalent of 1 football field. Like the.
What you're saying is if you were to absorb a gas.
Yes.
And treat the
Okay, I should be.
surface that is sitting on, that area would be.
Yes. So I'll tell you what we do generally for these materials, for most porous materials, we use this technique called N2 physisorption. Okay, it's called BET. It's an instrument where you put gas into these things and see how much gas it takes. And we usually assume it's monolayer adsorption, but it's obviously not monolayer absorption. But we use that that number to say that this would be the surface area, like a monolayer adsorption, that would be equal to that much. So to compare for the field. Okay. So typically to determine the area of these, the surface area of these things, we fill it with gas. We fill the volume with gas and then assume that it's forming a monolayer and using that to translate into the surface area. Okay. So then these MOFs, okay, this was the first, so you are going slowly from being it useless, then for it to being somewhat useful, and then now for it to being thermally stable. So in these particular MOFs, this is made, it's called UIO 66 because University in Oslo, or University of Oslo, I'm not sure, everybody who names this will name it in a certain way. They like if they found it in like HK, there's a MOF called HKUST. It's Hong Kong University of Science and Technology. They made a MOF which is very excellent. So they usually give the name of that because these things are a big deal. Like the moment they make them, they patent them because there is money to be made. Okay. So this particular MOF is very good because you have this zirconium oxide linkage and this zirconium oxide linkage, and you can change the length of this linker again. The same thing that we saw earlier. And these benzene rings, you can have functionalized groups. You can have amine groups or NO2 or something else, so you can coordinate better. Okay. So you can change the linker. You just change you take the linker, you put it in zirconium chloride, heat it in DMF, you got them off. You have to maximum do it like say 48 hours, 24 hours to 48 hours. And we used to make this regularly. It was not, you can give this as an undergraduate project. Anybody can make this as long as you have the chemicals. And you will almost always get the same structure. So that's one advantage of these compounds, okay? The ease of repetition, and you can validate it. Anybody can validate it and get the same material. And they will get the same values if they have access to a BET machine to find the surface area. Okay. So this particular MOF, what happened was, so this MOF, I just wanted to give you an idea of how it's become very popular. And it's been used for catalysis a lot, which is what we do, like what I have been doing when I was in my PhD, right? This particular paper is a collaboration between Professor Yaghi and the late Professor Gabor Samurjai, who was, I think the only thing he had in one is the Nobel Prize. He's considered the father of surface chemistry along with Gerhard Ertl, but mostly he had developed a lot of techniques to study surfaces, okay? So this particular MOF, what you could do is you could change the acidity of these linkages, right? You can put certain functional groups and you can change the acidity based on whether it has a proton or not, and then use them to do cracking, okay? And they tried with MOF where you can load the platinum inside the MOF within the pores. If you have the right linkage, for example, if you have NH3, it will coordinate to a platinum atom, and if there are enough NH3 linkages, you can control the amount of platinum that is there. And you can exclusively put it inside the MOF. There's a difference between putting the platinum, I've shown you a bit why it's important to put the platinum inside the MOF, okay? Because this MOF network can also form as a restricted environment. If you want to have a reaction, particular reaction to happen selectively, the particle has to be inside because the whole MOF is acting as a gate to what kind of bonds or what kind of moieties on the organic substrate can access the catalyst, the actual catalyst, okay? If the platinum is outside, it's just going to hydrogenate everything. Platinum is a very well known catalyst industrially, but it doesn't have any selectivity. Just if you put any molecule on it, it's just going to break it, and I'll show it to you in a bit. So yeah, this is a typical MOF. It's around 400 nanometers. Depends on the conditions you use. You can get like really well. You can get single crystals also of these particular types of these molecules. Okay, and they have reasonably good surface area. This particular MOF doesn't have very high surface area, but it's much better than a zeolite. It has around 1,200 meters squared per gram, but it's mainly used for catalysis. So yeah, so they tried with these different compounds. Like for example, if this is a control catalyst, okay, if you just put platinum on silica, you'll mostly get hydrocarbons, like only these acyclic isomers. Okay, you won't get cyclohexane, you won't get benzene. Whereas if you play around with the acidity, if you change the functional groups, you can change the distribution of the products. You can get more cyclohexane and more benzene and more aromatic compounds and reduce the amount of acyclic isomers. Like for example, in this particular case, where you had a sulfide linkage and you had SO3H, you can exclusively make sure no amount of this acyclic isomer, like linear chain hydrocarbons or branched hydrocarbons forms. Okay. See, with platinum, there's no control. Okay, it almost always gives you acyclic isomers, right? Like these things. Okay. But whereas when you do these UIO, when you put the platinum nanoparticle inside the MOF, you can selectively control it to give you either cyclohexane or benzene. Okay. And they try to increase it. Like even in this particular case, they had an SN linkage. They got more benzene than they got cyclohexane. So you can tune the nature of the product that forms when you're starting with methyl cyclopentane. Yeah, methyl cyclopentane. Okay. Starting with this, you can crack it to get different products. Okay. These are not valuable, but all of these are valuable. This one, the problem with platinum is you cannot control what fraction it is. It will usually break it up into any number of things. It can even give you gas, like methane, and that's completely useless to us.
I don't know if I missed it, but how is the tuning then?
So by changing this acidity and this platinum, like with the platinum linkage, right, with the platinum that's inside it, it can control the way it adsorbs on the platinum, like restrict the adsorption on the platinum in certain modes. Like you will not, I think I'll show it better in the project I'm doing. But basically what I'm saying is, with these, when you change this acidity of these linkages on the linker, right, when you have these particular things, it takes part in the catalysis. It acts as a co-catalyst along with the platinum nanoparticle, and forces the adsorption of the incoming substrate in a particular way so that only a certain product can come out. So by changing the acidity, they showed that you can get different kinds of products. Yeah, so this is the work we published. We did this in, we published this paper in 2014. So here what we do is like by controlling the place where the platinum nanocluster is within the MOF, you can restrict the access of all the bonds of this particular molecule. This cinnamaldehyde, okay? You have a double bond here and you have a carbonyl bond. Typically the value in industry for most of these alpha beta compounds, unsaturated compounds, alpha beta unsaturated aldehydes is that we only want to get this converted to hydroxyl group, okay? But most catalysts, the problem is you have to make like a bimetallic catalyst, or you have to dilute the amount of platinum or palladium, the active transition metal. You have to dilute it so only this bond hydrogenates. Whereas in this case, using a UiO66NH2 MOF, we got platinum to do what it never does. It only gives you this compound, where the double bond is still intact. See, because this kind of starting compound, right, is very useful for many pharmaceutical applications also. If you want to make sure only this bond is hydrogenated. Of course, we still got only 90% selectivity, but this is good enough. In this particular thing, normally when you put hydrogen and platinum catalyst, all these bonds will get hydrogenated. You'll get this, you'll lose this unsaturation and you'll get alcohol. You'll typically get this compound in just if you expose platinum by itself, okay? So this is very difficult to do. So in this particular thing, what we did was we controlled the loading of the MOF. We converted first to getting this UiO66NH2 linker. Then we bound it with the zirconium oxide, zirconium chloride, and we made the MOF. And the platinum was exclusively inside the MOF. First we load it as K2PtCl4. We take the platinum precursor, we load it into the MOF, and then we reduce it under hydrogen. And when it reduces, we can control the size to like 1 nanometer. See, this is not even a nanoparticle, it's a nanocluster. Okay, that means the amount of surface area of this platinum that you're using all of the platinum, the precious metal that is there, you're effectively using it all. Okay, normally platinum nanoparticles will be like say 5 or 6 nanometers or larger when you make it in any other method. But this method where we loaded the precursor first inside the MOF and then control the size, because of the environment, the encapsulating environment that the MOF gives, you could strictly control it to like 1 nanometer. Okay, of course the people, when the reviewers saw this image, they didn't believe us. They asked us to do TM by rotating the sample and seeing all across the ways. Like you have to show a 3-dimensional video of how the thing actually is inside. Because when you look at this 2-dimensional image, you cannot see. It could be outside the platinum nanoparticle, right? But we did all that and we proved to them that it is inside. And then we showed that it could be stable for almost 10 cycles. You can recycle the catalyst 10 times. Keep on reusing it, okay? And one more advantage of these MOFs, in this particular MOF, especially UiO66NH2, you could go from a loading of 1% to 10%, and we even tried 40%. It's still 1 nanometer, okay? Because there's that much space inside the MOF to contain these nanoparticles, to contain these platinum ions, and when you reduce them, you'll get the particular size, okay? But in a typical support that we use in the industry, when you use silica or alumina, which is commonly available, you can probably buy it on Amazon also. If you try to put platinum and put a 40% loading, you'll get big particles. So when you get big particles, it's of no use because you're basically taking a precious metal and you're wasting the amount of surface area that's accessible to the substrate or whatever catalyst can be converted into a product. Okay. So one more experiment we did was we wanted to show them that this structure where you have this platinum inside the MOF, it restricts the access of this bond, this double bond here. Only this carbonyl bond can go through. So we tried these 3 substrates. If you had it inside the MOF, only ethylene would go and will get hydrogenated, okay? Whereas for your cyclohexane and your 1-hexene, you couldn't do it, okay? Whereas on the MOF that is outside, you could get all of them, okay? Like you get equal amounts of all of them. And the conversion is low here because here this PT is a larger size. It's like at least 5 to 6 nanometers. Like you cannot differentiate between the hydrogenation of any of these compounds, okay? But in the case of when it was right inside, you could focus on the hexene and only the last bond which is there available to going to the window where the platinum nanoparticle is. So then we use it to also do another hydrogen transformation where you can again convert only this to alcohol. On typical platinum, you don't get good selectivity. This compound breaks down into all manner of things. Okay, you'll get like CHO, you'll get like furan, you'll get all the undesirable things, you won't get furfuryl alcohol. This is also a very important starting material, not of the organic industries. Here what we did was just included tin And again, we could control the size to around 1, like here 3 nanometers maximum. Okay, and it was inside the MOF. So yeah, now I'm going to go to a very important aspect of MOFs, especially, so I've spoken about catalysis. I'll cover just a few areas, okay, like water generation, gas capture. The other, there are many more applications. There are therapeutic applications of MOFs. There are biomorphs. Okay, and there is one more application I'll cover is regarding capture of uranyl ion from the seawater. But the most important most important application of MOFs is for gas capture. Okay, by changing the kind of organic environment around the MOF, you can change changing the kind of void that is there inside the MOF, the pores, the coordination of chemical environment. You can change the type of gas it's preferentially absorbing. Okay. Yeah. So before I go into that, I'll just give you a typical thing about this is how flue gas is treated. Yeah. Yes, I think there are applications for optoelectronic devices. There are many. The physics people use a lot of MOFs for a lot of, but I am not familiar with them. But there are applications. I just don't know. There are many papers on those for electronic, even battery materials and everything. Okay. So I'll just talk about flue gas. Okay, like typically when your coal plants and all this, you have a lot of CO2 being emitted. That CO2 is typically sent out into the atmosphere. That flue gas usually has only 12% of CO2. Apart from CO2, it has a lot of nitrogen, and it will have some amount of SOx and NOx gases like sulfur dioxide and nitrogen dioxide, or other versions of those gases. Okay. So typically what happens in industrial facilities is they try to capture it using these amines, these monoethanol amine, or these types of liquid amines, which have to be replaced over a time. And if you've seen these plants, they're huge. Okay. And over time, this compound degrades. When you have this gas which is coming out of this, it's at least 100 to 150 degrees Celsius. Like they have to cool it first. So you're wasting energy trying to cool that gas down, whatever the flue gas is coming out. Then once it comes into this amine scrubbing facility where you have this liquid amine there, it's reacting with this. If it's not cooled down sufficiently, it's going to degrade the amine. Okay. And then when you need it back, again you heat it to get back the methane or what. You can either do it through mediated to get biomethanation, but typically it's trapped as bicarbonate. If you want to release it, you have to heat it again. So all of this is a very energy intensive process, okay, and it kind of degrades the material that is already being used to capture the CO2. So as an alternative, you have this MOF is the reason I'm showing this particular MOF. It has arrived at commercialization and is being made in large scale quantities. BASF and this company called Swanta in Europe have commercialized this, and they're selling it for people who want to use this in their facilities. Okay. So this particular MOF, again, can be made very quickly, can be made in kg scale quantity without any problem, and it requires a very simple, it requires this ligand, and then you have some zinc salt, and you can make this linkage, and they have this interparallel thing where you have a zinc oxalic acid linkage in the middle. On top, it's one layer where you have this zinc and this coordinated weakly, okay? And then you have these layers in between, they're connected through these oxalic acid linkages, okay? But this MOF, the unique thing about this MOF, and the reason why I'm showing it is, it has a preferential adsorption for CO2 over water. So most of your gas that comes out from the flue gas, it will have high humidity, it will have a lot of water vapor, okay? And most of these MOFs, if you subject, even zeolites, okay? If you subject them to all the previously known MOFs, Al fumarate and zeolite 13X and CaU10, all these are well-known MOFs for CO2 capture. If the gas that's coming out has a large amount of humidity, it has a large amount of water, it will stop performing. It will not capture CO2, it will preferentially capture your water, okay? But this particular MOF, right, it had an ability to capture at least up to in 40% humidity, in 20% humidity, it was still capturing preferentially only CO2. It is slightly hydrophobic. Okay, what was happening was the way it was designed, each pore, water could only absorb on certain facets, and it couldn't form hydrogen bonding that much extensively inside the pore, and the CO2 would be exactly at the center. Okay, it is a very weak linkage, it is a very weak van der Waals interaction where it is not bound strongly. Most of these other MOFs, right, like CaU10, Al fumarate, and zeolite 13X, they have chemical adsorption of the CO2. So you capture the CO2, but then you have to heat it at say 200 or 300 degrees Celsius to release the CO2 again, because it's a very there's a strong chemical interaction between the bonds of that particular material and the CO2. Here it's not like that. it's more like a weak interaction. It's right at the pore. It's not bound to any of these atoms. There's no strong coordination. So you need to have a very little temperature, like within 100 degrees Celsius or something, you can release the CO2 back. So one of the advantages is the reason why it's been, commercialized so fast, it fits all the criteria of a good material that reduces the energy demand, quickly absorbs and desorbs CO2, and can be very stable for long conditions underwater. Like even if you put large amounts of steam, it's stable. Like they did the test on this, and they repeated through many cycles. Okay, they did like steam for 24 hours, 72 hours, 1 week. The activity stayed the same. Okay, its amount of ability to capture the CO2 in the presence of water was very stable. Okay, it was not a very high surface area MOF, but it performed the purpose that it was built for. Okay, so this is the prototype right now, and it's very cheap. All the materials that are involved in making this particular CALF20 is relatively cheap. You can scale it up very fast, and it's being sold by this company called Swanta. BASF and Swanta have combined together, and they're trying to do this. So what happens essentially is you have your flue gas coming in, you have your CO2 and the N2 going into the MOF. The CO2 stays. Okay, it stays there unless you want to heat it at a light temperature, like say 800 degrees Celsius, or just 100 degrees Celsius. It'll release it. And this MOF is stable in that steam and CO2 mixture at even at 150 degrees Celsius. Okay, so this is the first MOF that has actually been commercialized, and it's probably going to be used in any of these facilities where you have a flue gas facility right next to, and they want to bring down the amount of emissions they put out into the atmosphere. Yeah.
Are they using this in direct air capture also?
Yes, direct air capture also, but see the problem with direct air capture, right? You don't know, you're spending energy to bring air, you're spending a lot of electricity into building these huge fans to circulate that air into this. But this is very good for that also. So it will select the CO2 specifically and bind it.
Low concentration.
Yes, at low concentration. It's very selective to CO2. But the application of this particular MOF, they initially built it for flue gas systems, like where you have a lot of humidity in the thing that's coming out. Like you don't have to, see earlier what you would have to do is, even in the facilities where I was showing you, right? Where is it? Here you have to remove the water at some point. You have to cool it down, bring it down to a certain temperature, remove as much water as you can. Otherwise that also affects your, eventually, like if you have that hot steam coming in. Here they tested it with the steam. So they don't have to do any purification step. They don't have to cool down the gas. They can just pass it directly into it, right? Okay. So this is one MOF, and this is the one that's commercialized right now. It's being probably going to be used in a lot of places where they do flue gas capture or even in direct air capture.
So, if I
Yeah.
sorry to interrupt. You might have already covered it before I came in. Sorry, I came in late. How energy intensive is the production process?
It's not, like it's just solution. Like you can just mix the chemicals in water. At the most you need, like, the only problem is that you might have to use some solvent like DMF.
Okay.
You'll have to use a DMF, dimethylformamide. But then you can always reuse that solvent. Once you make the MOF, it usually precipitates out. It's a solid powder which can be easily separated from the solvent, and you can recycle the solvent. And some of the temperatures that they use, like 100 degrees Celsius, even if you scale it up. So in that sense, it's better than making most of your liquid adsorbents, which are actually very energy intensive. So these solid, and all the materials are kind of very, like the zinc salt that they use for this and the oxalic acid, everything is very cheap. It's not very cost intensive. So yeah, then people have tried, this is another paper where they have made this, they had some problems publishing this paper because they were already, the company that published the other paper, the science paper, they had already patented the molecule, the CALF20, right? But they still got permission from them and they did this. It's like another application where you put it in lignin and you can use it, you can even increase the surface area even more. Instead of having all the powders together, you can spread it out even more on this lignin and then show its application for carbon capture, CO2 capture. Yeah, this is another MOF, also for the same purpose, okay? Here, what is the funny thing about this MOF is, it operates only at high temperatures. Okay, like you don't have to worry about this MOF. This MOF is stable up to 600 degrees Celsius, and it has this specific reversible zinc linkage. Okay, it'll have these blue atoms are zinc. It has like a particular linkage which will be replaced by the incoming CO2 and forms formate on it, and the formate will stay there once it comes and goes. Okay, so you have this reversible bonding where you have this zinc. Initially, there's only a hydride. Okay, but when the CO2 comes in, you have this formate forming immediately on the zinc atom, And then when you want to release it, you can just heat it and release it. Very low temperature. You don't have to heat at a very high temperature. Okay. But this process, the advantage is it happens at around 275 degrees Celsius. See, at 25 degrees Celsius, it doesn't happen, right? Like when I told you guys about the amin, you had to cool it down. Here again, you don't have to cool it down at all. Sometimes the flue gas stream can be even more hot than what we expected, like 200 or 300 degrees Celsius. This MOF becomes active only at 275 degrees Celsius because at this temperature, it can overcome any thermodynamic barriers and actually adsorb it. It's not that much, the energy requirement is not that much compared to when you do that to 25 degrees Celsius. Okay. So this particular MOF was, it was published in Science because of its usefulness. Like again, you're saving the energetics of the process where you don't have to cool the flue gas. It's coming right out, you don't even have to purify that gas. Whatever is coming in will only the CO2 will adsorb on this at 275 degrees Celsius. Because at that temperature, the energy requirements are met to overcome any thermodynamic barriers. Right? So this is the last application I'll show of MOFs. This is also by, most of the work that I've shown you here is actually a direct consequence of the work carried out by Omar Yaghi. Okay, this particular paper also is, like he was a big fan of this, like he wanted to do this very extensively. He's gone to many desert locations in America and even in Saudi Arabia and other places, where they've tried to show MOFs as a source of capturing water from high humidity areas. Okay, like I told you, like there are MOFs which can capture gases, and there are also MOFs which can capture moisture from the atmosphere. Okay. So in this particular case, there's this MOF called MOF 801. Okay, it's again made from very, very cost-effective materials. You have aluminum as a salt, and then you have these compounds. And essentially, what happens is during the night when the humidity is very high, you put this thing open, and you have MOF loaded inside on this in this filter. You keep the slide open, and the desert air will keep circling into this chamber. Okay, and whatever MOF is there, it's very adsorptive. It takes all the water in from the air, and the air goes back out. In the morning, you keep it closed. When you keep it closed, what happens is because of this heating of this chamber, the water comes out as water vapor and it condenses on the walls of this. They put like videos and all of this. Okay, and they've done this where you can have this bottle. They've designed a bottle. It's just that it sometimes starts to fail when you go to higher temperatures. Higher quantities, like if you want to do it on like kg scale quantity. So it's still it's a concept. It's not fully developed yet. They've been able to show it for like small scales. Okay, when you start industrializing a process like this, adsorption of that water introduces more heat, and that makes the material more unstable. Okay, but then ultimately they've proved that you can use it to collect water from the air. Yeah, they've put like the whole setup and they've shown how they can use these MOFs to collect water. And that water is actually potable water. Like this could be very useful in places like Saudi Arabia, where you don't have access to proper drinking water in many places. Okay, they basically rely on desalination to get all their drinking water supply and everything. Whereas if you had this, yeah, and then this is another example. Say this is another MOF where you can convert the linkage. This is called post modification. After you make the MOF, you can change this particular linkage, or you can add on to it. Okay. They made amidoxim. They started with cyanide, and then they got this amidoxim MOF, and this is very selective for uranyl capture from seawater. See, in the seawater there is not much. There's a very small concentration of it. Okay, but if you could selectively get all of it, a lot of that uranium can be used. Like this is one application. I don't think it'll probably never reach commercialization in our lives, but it's one way of looking at. I don't think even uranium is that much, the concentration is not that much in the world.
Parts per billion in the field.
Yeah, but if you collect it and keep on, there's overall, I think you can get as much as possible. So, but it's parts per billion, but you can use these MOFs to selectively take. Yeah. So typically, and they adsorb very fast. They adsorb the uranyl very fast, and then you can convert it. Okay, because I think uranium is, it's not, in the next 100 years we have uranium supplies in many parts. Right? I don't think we have infinite deposits of.
But we have a lot.
Yeah. Okay. So again, I just want to show that these MOFs can also be used for these kind of captures, for these like selectively taking only the uranium from the seawater. Okay. Here, what there is, there's another thing. It's a very popular thing in MOFs. They call this defect engineering. Okay. Like initially, when you make a MOF, you have to put an equal ratio, a stoichiometric ratio of that linker and the salt, the node, which is forming the metal node, right? Sometimes you can change the ratio. You can put less of the linker what will happen, the MOF will still form, but you'll have these vacancies where the linker is missing. That linker site, it's called a defect. And that defect site can, for example, here what they did was they mixed zirconium and titanium chloride, right? So you have a photocatalytic node and you have a linker, you have a spot where you don't have a linker. So there are energetics can happen through photocatalysis here. Okay, so they've used this also to convert this uranium, which is usually soluble, into the insoluble form. Okay, so these kind of things can also be done with MOFs. They can do catalysis and adsorption at the same time. So photocatalysis, there are many. I have not put any applications of photocatalysis in this particular presentation, but MOFs have been used for a lot of artificial photosynthesis. Okay, so yeah, there are numerous applications. I've barely covered it. I just wanted to show you that what these three people have started has opened up so many arenas. Like, the number of papers published in MOFs is humongous every year. In fact, the paper that I have, the one paper that I have on MOFs, that's probably my most, it keeps getting cited because it has applications. People are constantly looking for applications of these materials. Okay, and they're so easy to make, right? Until somebody discovered them, nobody knew their value. But now that they've been found and there's so many people are writing on this and so many applications are there. Like, I haven't even spoken about any of the diagnostic and treatment options. There's another person in University of Chicago. He's called, his name is Professor Wenbin Lin. He does a lot of work on therapeutics using MOFs. Okay. And yeah, for drug delivery, then you have gas storage, of course, I've covered. Catalysis, I've covered. Energy conversion, like you were talking about magnetism and optoelectronics and all this, right? MOFs find application in that too. Okay. So there's literally no area that MOFs have not been used in. It's just that I cannot cover all of them now. And I think you can all go look it up. So I'll briefly talk about something else, okay? So it's called covalent organic frameworks. This is like, it happens kind of, this is again something Yaghi discovered. And he's been proposing this also as a way. These are also very good materials for gas capture, okay? Here you completely remove the metal node. You're using these linkers where this particular linker, it's like it's a amine linker and then you have a carbonyl group sometimes, or you have a boronate ester kind of group. You can form these temporary linkages, like imine linkages, okay? Just using this, but mostly the problem with these things is they just form 2D layers. They form two-dimensional layers and then you need to stack them up through pi-pi interactions to get the overall powder. Ultimately, it forms a powder if you make these materials. But the advantage is you don't use any metal here. Okay, but these are not as stable as MOFs yet. They will take some time to catch up. A lot of papers are being published on them, but they also have the same sorption capacities. They can try to capture CO2, and based on how you modulate this, right? You can use various types. These are all the different types of ways you can make these linkages, okay, to form a 2D material, okay? This is one that is most popular, and this...
They are all covalent organic frameworks.
Yeah.
The solvents are bound by covalent interactions. Why are they not strong?
Also, but like the thing is, only that layer, right, is strong. But in between, like one 2D layer will be fine. You'll have this like linkage. I'll just show one of these. See, this is a typical KOF layer. So for this, it has to be stacked with another one on top to have weak van der Waals interactions.
So the covalent only
is only in the linkers here.
Not between.
No, it's in between layers. It's like a...
The interaction between layers or the binding between layers or through the metal node.
No, there's no metal node here.
No, not here, but in your.
There it's metal node, yeah. There it's a coordination linkage, a proper coordination linkage in between layers. You'll have the nodes interconnecting layers. Here there's no metal at all. And the problem with these things is right now the biggest problem is some of these linkages, right, they reversibly break. So based on the kind of solvent you use or the kind of application you use it for. So they're still picking up. There are people who are making three-dimensional KOFs, but that's kind of difficult. Already this is hard. And getting this to be stable is hard. But it's slowly picking up, and maybe sometime in the future, because if you don't need metal, it's even better. But metals, most of the metals used right now, aluminum, zinc, they're abundantly available. So MOFs will never lose their value because of the fact that we use these relatively cost-effective metals. Okay. So yeah, if you have any questions, I just basically talked about how these materials can find more and more use in the future. Okay, the developments are immense. The options for them to be used in a wide scale are great. Of course, for them to be used in the scenario, like for the environmental application or something, there has to be some amount of policy level involvement. Like in Saudi Arabia, they're like big fans of Omar Yaghi. I think they've given him honorary citizenship, and he's involved in their massive plans for revamping their cities in terms of sustainability and everything. So it has to be some amount of government involvement to get this to be more widely adopted. Like CAF 20 is now being sold commercially, right? So it's up to people to adopt these technologies. Any questions?